Consider the following situation. Steam enters a turbine at 6,000 kPa, a temperature of 400 degrees centigrade, a velocity of 10 meters per second, with a mass flow rate of 4,600 kilograms per hour. The turbine produces 1,000 kilowatts of mechanical power. The fluid then exits the turbine at 10 kPa, a velocity of 50 meters per second, and a quality of 90%. We want to calculate the rate of heat transfer between the turbine and our surroundings in units of kilowatts. We begin by writing our state variables. At state 1, we have a pressure of 6,000 kPa and a temperature of 400 degrees centigrade. Thus, we are existing as a superheated vapor, i.e. our quality at state 1 is undefined. Our velocity at state 1 is 10 meters per second, and our mass flow rate is 4,600 kilograms per hour. At state 2, our pressure is 10 kPa, and since we have a quality of 90%, our temperature at state 2 is equal to our saturation temperature with a corresponding pressure of 10 kPa. Our velocity at state 2 is 50 meters per second, and since this is a single stream steady state device, our mass flow rate at our exit is identically equal to our mass flow rate at our inlet. We will start by expressing our conservation of energy equation for a single stream steady state device. Our time rate of change of energy is equal to 0. Thus, 0 is equal to the rate at which heat is supplied, Q dot, less the rate at which work is done, W dot, plus our mass flow rate into our system, M dot 1, carrying an enthalpy H1, a kinetic energy V1 squared over 2, and a potential energy GZ1, less our mass flow rate out of our system, M dot 2, carrying an enthalpy H2, a kinetic energy V2 squared over 2, and a potential energy GZ2. Now, if we neglect our potential energy contributions within our system, we can rearrange our expression for Q dot, recognizing M dot 1 and M dot 2 are identical. Thus, Q dot is equal to W dot plus M dot times the quantity H2 less H1 plus V2 squared minus V1 squared over 2. We know W dot and our velocities within the system. Thus, we need to determine our enthalpies at state 1 and state 2. At state 1, since we recognize our fluid is existing as a superheated vapor, we pull our enthalpy value of 3,177.17 kilojoule per kg directly from our tables. At state 2, we will solve for enthalpy based upon our saturated liquid and our saturated vapor specific enthalpies taken at 10 kPa. Thus, our enthalpy at state 2 is equal to our saturated liquid enthalpy at 10 kPa plus our quality times the difference of our saturated vapor and saturated liquid specific enthalpies taken at 10 kPa. Thus, our enthalpy at state 2 is equal to 2,345.35 kilojoule per kg. Now we can substitute all our known values into our conservation of energy equation, ensuring proper conversion of units for mass flow rate and our kinetic energy contribution. Thus, Q dot is equal to W dot, which is 1,000 kilowatts, plus M dot, where we have to convert 4,600 kilogram per hour to kilogram per second by dividing our quantity by 3,600. Thus, we would have kilogram per second. And our mass flow rate is times the difference of our enthalpies and kinetic energy contributions. Our difference of enthalpies, H2 less H1, would be 2,345.35 less 3,177.17 kilojoule per kg, plus the difference of our kinetic energy contributions. Thus, at state 2, our velocity is 50 meters per second squared, less that at state 1, 10 meters per second squared, divided by 2, but we have to convert our meter squared per second squared to kilojoule per kg. And we do this by dividing this quantity by a factor of 1,000. Solving for these values, Q dot is equal to minus 61.347 repeating kilowatts. The negative sign indicates that we are rejecting heat from our control volume to our surroundings.